Hello and welcome again as we look at yet another multiple choice question for IB chemistry. This one is particularly tricky and it serves to highlight why it's so important for students to take some time in their preparation for exams and set that time aside to work through multiple choice past examinations. Because suppose you've finished studying section 20.1 of the IB chemistry guide and you feel that you've really understood SN1 reactions, SN2 reactions, all about the structure, all about Markovnikov's rule and the carbocation, about the need for polar solvents in both of them, but for aprotic solvents in one case and for protic solvents in another case. You also added information about the leaving group, remembering that bromine is a better leaving group than chlorine, and chlorine is a better leaving group than fluorine, and iodine is the best of the halogens when it comes to leaving groups because it forms the weakest base of them all, which makes it the best leaving group. The thing about it is, when you bring all of that and you look at a question like this, you could find that you're coming up against what seems like a huge roadblock. And if you don't pay attention to one simple fact that's not particularly highlighted anywhere, then you'll be frustrated. You'll lose time in the examination. 90 seconds would go by, 2 minutes would go by, and you'd still be stuck on this question. But if you take the time out to practice and see that little point that's needed, then this question could be done in 20 seconds. So let's take a look. Halogenoalkanes can undergo SN1 and SN2 reactions with aqueous sodium hydroxide. Which halogenoalkane will react fastest with a 0.1 moles per dm cube solution of aqueous sodium hydroxide? Well, the first thing you have to be able to do with this question, of course, is to take these four structures and have some idea as to what each one looks like. Without me actually drawing them out though, I can tell that this 2-chloro-2-methyl-propane, this is going to give me a tertiary halogenoalkane. And if it's going to give me a tertiary halogenoalkane, then I should know that it's going to have a carbocation that is going to be well stabilized by 3 methyl groups. But let me draw that so you can have a look. So here you have it. 2-chloro, 2-methyl-propane with 1, 2, 3 carbons and everything saturated. This carbocation would be stabilized by the inductive effect, the pushing of electrons. This 2-iodo-2-methylpropane is the exact same structure, just that it has an iodo instead of a chloro. Now, what you should know previously is that iodine is a better leaving group than chlorine. So therefore, if you compare A to B, then you know that B, because it has iodo instead of chloro as the leaving group, B would be much faster than A. So now you know that B is a possible answer and A has been eliminated. Now looking at C and D, you'd realize that they are not tertiary halogenoalkanes. 1 chlorobutane and 1 iodobutane would look like this. 1 iodobutane has this structure here. 1, 2, 3, 4 bute, 1 for the iodo on carbon 1. So 1 iodobutane. This is a primary halogenoalkane. And you should note that primary halogenoalkanes would have SN2 reaction mechanisms. And when you have a primary halogenoalkane, the steric hindrance isn't that much, so therefore you should expect a pretty good reaction rate here with sodium hydroxide. Now, how are you going to decide whether the SN1 reaction is faster than the SN2 reaction, this here being the SN1 reaction, this being the SN2? What information do you have about actually comparing the rates of each one? Especially when you have this here that's stabilized by a tertiary carbocation. Here you have steric hindrance pretty low because you have a primary halogenoalkane. Here, of course, you can eliminate C for the same reason that you eliminated A. We have said that iodo is a better leaving group than chloro, so iodo would eliminate chloro. And how would you choose between B and D? Which is going to be faster? And you have to reflect on what you know about the solvent. What type of solvent is needed for an SN1 reaction, and what type of solvent is needed for an SN2 reaction? This SN1 reaction requires the formation of a carbocation, and the hydroxide, you recall, has to be kept under control. It has to be kept in check. It has to be surrounded by something that's going to hydrogen bond to it. It needs a protic solvent. Both of them need polar solvents, but the SN1 reaction, where you have the rate of the reaction dependent upon this single molecular entity, the carbocation, that has to take place in the presence of a protic solvent. But where's the information about the solvent in this question? Do we have a protic solvent, or do we have an aprotic solvent, which would favor the SN2 reaction? The answer to that is in this underlined term, an aqueous solution of sodium hydroxide. An aqueous solution implies that sodium hydroxide is dissolved in water. And because it's in a solution of water, that of course implies that you have a protic solvent. And with the protic solvent, then it means that reactions like C and D, which require aprotic solvents to be favored, would be very unlikely to happen. And then of course the rate of the reaction would be much faster with these two. And of course, with the better leaving group being found in B, the answer to this question is B.